So section 3.3, Kramer's rule. Let's see how far we can go up with this section today. This is basically application to what we learned in the last two sections. We learned about determinants, their properties, and today we're going to apply the determinants here in an actual mathematical application. So what the Kramer's rule says, Kramer was able to find a way to calculate to solve systems of equations. If you remember in Algebra 2, we teach how to solve two equations and two unknowns, or three equations and three unknowns. Now, to solve two equations and two unknowns, people say, okay, I can use elimination. So like if you are asked to solve 3x minus y equals 1, negative x plus 2y equals 0, yeah, you can do elimination, or you can use substitution, or you can use graphing method. In either one you can solve it, but we're not concerned about this. We're concerned about if they give me a system of equations, let's say like 10 equations with 10 unknowns, that will take you hours maybe to find it out, and then with any tiny mistake it can get you nowhere with the solutions. So the idea here is we use determinants to show you how powerful determinants can be to help us solve this kind of problems, like 10 by 10 by 10 with like 10 equations with 10 variables. I mean, it's not only 10 by 10, it could be 5 by 5, anything. So what Kramer's rules says, so Kramer's used the determinants to help solve systems of equations. He said, let's say we have a matrix, a square matrix A that is invertible. Invertible means its determinant is not zero. Then for any vector B, any B in Rn, there is a unique solution. X of the equation Ax equals B has entries with solutions. Xi can be calculated by finding the determinant, and then when we show you the example will look much easier than seeing this notation here. Determinant of Ai at B over the determinant of A, where I ranges from 1 to n. So Ai of B is Ai B An. So this is the ith column. You might be confused to see this notation for a minute, but let me show you example what this means. If I need to solve this system, x plus 7y equals 0, x minus 4y equals 11. To solve something like this, first we write the matrix A down. The matrix A can be formed by taking all the 1, 1, 7, negative 4, those entries, the main coefficients of x and y. Then we can find its determinant by multiplying across the main diagonal minus the other one, so that's negative 11. Now A1 of B, watch what we do. A1 of B means in the first column, we do not use 1, 1 anymore. We cover them and use the 0, 11 instead, but the second column stays the same. Then its determinant is 0 minus 77, so it's negative 77. Do you guys see what I did? That's what I meant by the ith column. So when I say A1 means the first column. Now we do the second column, A2 of B. This means I leave the first column the same, and the second column get replaced with 0, 11. The determinant in this case of A1, A2B is 11 minus 0, which is 11. This will get us to find what x and y are. So you can call it x1, which is x, is the determinant of A1B, or of B, over the determinant of A, which is negative 77 over negative 11, which is 7. And x2, which is y, is the determinant of A2B, or A2 of B, over the determinant of A. A2B is 11, and this is negative 11, so that's negative 1. These are the answers for x and y. I strongly recommend you try another one on your own first. Let's come up with an equation or a system of equations. Say 2x plus, what do you want, 3y equals some number. Say negative x plus 4y equals 1. Okay, so how about something like this? Try this now. Okay, so now we can go over this one. Again, we need to find a first. So a is basically the coefficient of x's, the coefficient of y's. From here we can find its determinant, which is 8 plus 3, that's 11. Then we need to find a1 of b is, you replace the coefficient of the first column with 9, 1, and the other one 3, 4. So its determinant of a1 of b, it's 36 minus 3, which is 33. And a2 of b is, keep the coefficients, the first one the same, but we replace that with 9, 1. So then the determinant of a2 of b is 2 plus 9, 11. So then x, which is x1, is the determinant of a1b 33 over a itself, or the determinant of a, so that's 3, and y would be the a2b, determinant of a2b 11 over the determinant of a itself, so that's 1. Let s, how they make it more difficult, let s be a parameter that can take other values. Determine the values of s for which the system has a unique solution. Then use Cramer's rule to describe the solution for the system 6sx1 plus 4x2 equals 5 and 9x1 plus 2sx2 equals negative 2. So they want us to find S for which the system has a unique solution. Unique solution means we need to make sure, if you go back up to the Cramer's rule, it says here, the first thing says A is invertible automatically means the determinant is not 0. And why is that? Because if you look at the procedure here, when we find the xi's, we divide by the determinant, and we can't divide by 0 in mathematics. So that's why we have the condition that in order for this to have a unique solution, the determinant cannot be 0. So first thing we do, let's form a matrix A with coefficients 6s, 9, 4, and 2s. Then the determinant of A would be 12s squared minus 36. We need to make sure this is not 0. So you can divide by 12, so s squared minus 3 is not 0. So s squared cannot be 3. So s cannot be plus or minus the square root of 3. So s can take any value, any real number value, except square root of 3 and negative square root of 3. You can't use these two values. Now they said use Cramer's rule to solve this system basically. So we say in order for the system to have a unique solution, the solutions x1, x2 can be calculated as I showed you before. It's the determinant of a1 of b over the determinant of a. We calculated the determinant of a already. It's 12s squared minus 36. Now we need to find the determinant. Let's find a1 of b first. This goes as replacing the first factors with, or first coefficients with the constants on the right side, 5, negative 2, and keep the 4, 25 the same. So the determinant of this, it's 100 plus 8. Wait, that's 2s, not 25. That's 10s plus 8. So then x1 would be what we just got, 10s plus 8. And for the other one, we had 12s squared minus 36. Note here that 12s squared minus 36, you can take a 12 out, you get s squared minus 3. So x1, you can factor a 2 on the top, and we have a 12 times s squared minus 3. So by 2, 1 by 2, 6. So you get 5s plus 4 over 6 times s squared minus 3. That's for x1. We can do the same for x2. So we need to find a2 of b by leaving the first column the same. First column was 6s and 9, and replace the second column with 5, negative 2. So its determinant of a2 of b is negative 12s minus 45. Minus 45. So that gives us x2 equals the determinant of a2b over the determinant of a. And we found this negative 12s minus 45, and the other one was 12 times s squared minus 3. You can divide top and bottom by 3. You get negative 4s minus 15 over 4 times s squared minus 3. That's x2. Any questions about this? So we will continue. That's all we can get, like x1, x2 in terms of s. We can't actually get the numbers. We don't know what s is. It's just a parameter that can take any real value except square root of 3 and negative square root of 3. We will continue with this section next time. We are maybe a quarter way down, but we will finish the rest of it next time.